Here's an introduction to drag forces. Remember that a drag force happens anytime an object is moving through some kind of a fluid, through either a gas, the atmosphere usually, or liquid, water usually. And one important thing to remember about drag force, it always points opposite to the velocity of the moving object, the object that's feeling the drag force. The other important point about drag force is that as the moving thing's speed increases, the drag force gets stronger. Two ways to think about that. Magnitude of drag force might be directly proportional to the magnitude of the velocity, in other words, directly proportional to speed, or in different circumstances, if it's a different object and different fluid, the magnitude of the drag force might be proportional to the square of the speed, the square of the magnitude of the velocity. But either way, the most important thing to remember is that higher speed means higher drag force. And let's look at one of the consequences of that. Imagine that you just drop some object, could be anything, ball, rock, whatever. So just drop, let go, starts from zero speed, and then of course speeds up as it begins to fall. And let's say you drop it from a great enough height that we can see the behavior change as time goes by. Well, time zero, 0 seconds, when you turn on the stopwatch, at that moment, the speed was 0. So if the speed is 0, drag force is 0. Drag force acts only on an object that's moving. So 0 drag force means the only force that's acting on the falling object is the weight, mg. So in this case, at this moment, when the falling thing first began to fall, the net force is nothing but the weight. Right? The net force is equal to nothing but m times g. Now, the thing falls for a little while and speeds up, and because it speeds up, now it has some velocity, so now there's some drag force pointing opposite to the velocity. So a little while later, at a time t1, a little bit greater than 0, the weight force is still there and it hasn't changed, but now there's a little bit of upward or backwards drag force pushing against the falling object. This upward drag force cancels out part of the downward weight force, and now you've only got this much left over. After that cancellation, you've got only this much left over for net force. So now, at this later time, time 1, the net force is actually a combination of weight and drag force pointing in the opposite direction. And because now drag force has subtracted away, canceled away some of the original downward force from the weight, the net force at time 1 is less than the net force was way back at the beginning. Way back at the beginning, the net force was the weight, exactly the same as the weight, m times g. Now it's m times g minus a little bit of drag force. But still, there's net force down, so there's acceleration down. That downward acceleration is in the same direction as velocity, so the falling object continues to speed up. And as it continues to speed up, speed increases, so drag force increases a little more. A little bit later, at time 2, a little later than time 1, the speed has increased, so the drag force has increased. The weight pulling down hasn't changed at all. But now there's a stronger drag force in the opposite direction, so more of the downward weight gets canceled out, and there's less downward force left over for the net force. The drag force got stronger, and as a result, the net force got smaller. The net force at time 2 is now less than the net force was at time 1. That continues. There's still downward net force, so the falling thing is still speeding up. It's speeding up with a slower acceleration because the net force is smaller, but it's still speeding up. And since it's still speeding up, the drag force still increases until you get to a situation like this, where the drag force is almost as strong as the downward pulling weight. So the drag force is able to cancel out almost all of the downward force, leaving you with just a little bit of downward force left over to give you the net force. Now, because the drag force has gotten much bigger, it's subtracted more and more from the downward pulling weight, so the net force gets smaller and smaller. The net force here at time 3 is less than the net force was at time 2. But there's still a little bit of downward net force, so the falling object still keeps on speeding up. Eventually, it speeds up enough so that the drag force increases enough, and at that point, the drag force increases enough to be equal in magnitude to the downward pulling weight. What's happening then? So at that time, we'll call it T4, a little bit later than T3. The weight is still the same as it's always been, still pulling down. But now the drag force the speed has increased, therefore the drag force is increased, now increased enough that it's now actually equal in magnitude to the weight. The drag force can completely cancel out the weight, because the two forces are opposite and they have the same magnitude. So now the net force is 0. Zero net force means there's no more acceleration, because net force is the thing that causes acceleration. So the cause of acceleration is not there, so acceleration won't be there. 0 acceleration. In other words, the velocity stops changing. The velocity stops increasing. The falling object stops speeding up. And because it stops speeding up, the drag force stops increasing. So the drag force just maintains this same value all the rest of the time that the object is falling. And so the net force stays 0 all the rest of the time the object is falling. So 0 acceleration during all the rest of the fall. So constant velocity during all the rest of the fall. 0 acceleration means a constant velocity. Previous to this moment, the falling thing had been speeding up. Now it stops speeding up and maintains that same speed the rest of the way down. And we call that constant speed that it has sped up to the terminal velocity. So when the drag force is big enough to cancel out the weight and give you 0 net force, when the and that force is 0, then the velocity is now the constant terminal velocity. Well, let's think about that a little bit more. That at this point, the drag force is equal in strength to the weight. That is, mg, the weight is equal to the drag force. And let's say that the particular kind of drag force we're dealing with is the one that's proportional to the square of the speed. That is, at this point, when the drag force is increased, so it's just as strong as this, and that drag force is b times square of the speed, well, that speed is the terminal speed, the highest value speed that that the falling thing is ever going to have. The highest value of speed will give the highest strength, the greatest strength for the drag force. That's the strength that's enough to totally cancel out the weight. So I'll just do a little bit of algebra there. Solve that equation for terminal speed. Divide both sides by b. And that gives us terminal speed squared. So in this case, the terminal speed is just the square root of all this stuff. Square root of mg over b. B, that was the proportionality constant in our expression for drag force. B is really a product of a whole bunch of factors, and we'll look in more detail in class at what kind of things are contained in B. But one thing to notice here right away, a bigger mass means a larger value for terminal velocity. Right? Bigger mass, so the numerator here increases, so this whole fraction increases. So the square root of that fraction increases, bigger terminal velocity. In other words, something that's falling, if it's more massive, it'll fall for a longer period of time, giving it more time to speed up to a higher terminal velocity. A thing with more mass doesn't achieve terminal velocity until later. And then when it does, it's a much higher terminal velocity. If you drop a feather and a rock, you'll see the feather almost immediately get to its terminal velocity, and you won't see the rock get to its terminal velocity unless you've dropped it from a great height and are able to watch it for several seconds, because the mass of the feather is tiny, so a very small terminal velocity, very little acceleration is needed to get to that very small terminal velocity. So it takes only a short time. Bigger mass means it'll take longer to get to the terminal velocity, because the terminal velocity is so much bigger, and that rock will need more time to accelerate up to the terminal velocity. And we'll have more to say on this in class.